So Mike, thanks for your willingness to give this talk. It's really great to have you here. As many of you will know, Michael is a full professor at the University of Alberta, and is also one of the lead scientists at DeepMind. I think he's very well known in the broader AI community for many contributions, ranging from works in computer games like poker, Hanabi, the Atari domain, and even sports like curling. And he has also made a lot of fundamental and algorithmic contributions to, for example, multi-agent reinforcement learning, using game theoretic concepts and principles. And I think his talk today will also touch, upon the latter, revisiting maybe some of the key equilibrium concepts used in COMARL. So thanks again, Mike, for agreeing to give the talk. And with that, I'm actually happy to hand over the word to you.
Great. Thank you, Carl. I'm pretty excited to be giving the inaugural, talk in this series. And I'm also excited because I get to share some fairly new work that I think is very cool. We'll see what you think. But I think it's cool because I want to question some of the very foundations that we often do in multi-agent RL, and think that maybe some of the blockers to our success is hindered by some of these often unstated choices that we make.
I think you accidentally muted yourself, maybe, Mike.
Excellent. Okay. I love technology. Okay, let's see. See if I can both not mute myself and advance my slides at the same time. Yeah, this talk is very much a collaboration. My PhD student, Dustin Morrill, is responsible for a lot of this. And one of the works I'm going to talk about is going to appear at AAAI next week. And so please check out the presentation from Dustin. If I'm unclear, I bet you he is not. I bet you he is very clear. But really this work started with Amy Greenwald giving a talk last year at AAAI at a workshop. And then there was about 200 emails that went back and forth after that talk. And now there's a paper at AAAI from that, and another paper that should be up on arXiv very soon. That's going to be what I talk about today. So you can check out the first one already. The second one, like I said, should be up and available very soon. Okay. Yeah, let's get started. So as I said, this is going to sort of be alternatives to Nash, but let me start at the beginning. We're trying to build agents. We want to build rational agents, intelligent agents. So, the typical place we might start with our notion of rationality is sort of pretty traditional, would be, well, we want something that maximizes utility or maximizes rewards. I'm going to bounce back and forth between a sort of a game theoretic terms and RL terms. I'm going to try to stay closer to the RL terms, but a few places I'll give the game theory notions of the same thing. But here we want to maximize rewards with respect to our beliefs, fairly traditional notion of rationality. But how does that play out in AI? Well, we build a rational agent of some sort. We build our agent. We imbue it with something that feels like rationality, and then we go and unleash it interacting with some environment. Let's just think single agent for a second here. Let's suppose we don't have to worry about other agents necessarily in the world. We're taking action. We're getting observations and some rewards. And so what would expect our rational agent to do? Well, it has some beliefs about the world, but as it interacts with the world, those beliefs will presumably then start to converge on what's correct and true, and eventually it'll understand how the world works. And so then maximizing reward is consistent with optimal policies, right? So the result of that interaction we might get out of that is a pi star, the optimal policy for this interaction. And so we see this in a lot of single agent work. I mean, I guess as a starting point, we see this in supervised learning, right? We gather a whole bunch of data, and then we see if we can learn the target concept. We see it in things like AlphaZero, where we have, well, let me go, that's a multi-agent case, but we see it in Atari, where we have agents that are interacting with an Atari game, and then after some amount of interaction, we go and see how well does it play that game. And we sort of see if we can set a higher score than somebody else. Okay, so this is a sort of our basis. So then what happens when we add another agent into the picture? Okay, so there's some other agent interacting with the world. But if that's a rational agent as well too, then we expect they're going to maximize rewards with respect to beliefs. So they're going to interact with the world. Eventually, their beliefs are correct about the world and each other. And as a result, we're going to get something like a Nash equilibrium concept, because all the agents are maximizing the reward with respect to their beliefs. And if their beliefs are correct, then we end up with an equilibrium concept. Let's just start with something simpler, though. So often a place we'll see this happening would be a zero-sum game. So I'm going to show a couple of matrix games in this talk. So you've probably seen these before, but in a matrix game, one player is picking the row of this matrix, and the other player is picking the column of this matrix. And then, if the row player picks a rock and the column player picks paper, then the row player gets a payoff. It'll be the first number, -1 in this case, so they lose, and the column player wins. Okay, so we can model sort of simultaneous single action interactions with these matrix games. So if we were to do this, then we end up finding, if we were to find a Nash equilibria, it ends up having some specific properties if the game is zero-sum like this is. If it's just two-player and the sums of the utilities add up so that whatever I win, the other player loses, then we actually have some nice properties for this, this pi star that we might expect to come out. That the properties mainly are that it's minimax optimal, meaning that the policy we'd get for one of the players guarantees it gets the game value against anybody else's, any other player strategy, whether they're rational or not. It's also interchangeable, that if there are more than one pi stars, then if I play my part of a particular pi star, it's still rational, and it is an equilibrium solution with another player's part of their pi star. And so I actually think this model that we take from single agent learning is still pretty effective. And we see it in things, as I mentioned, AlphaZero is essentially doing this as a way of training agents. And I think we've made a lot of progress in games that are two-player zero-sum because of this. OK, let's go beyond two-player zero-sum. Suppose there's 3 players, or the game isn't zero-sum. Then, if we still rely on this, then we end up kind of in the same place. We can still say, let's maximize rewards with respect to beliefs. We have a series of rational agents. Again, this concept of a Nash equilibrium still exists. Maybe pi star will pop out of this interaction. And that's good, I guess. Maybe we're happy with that, except for, well, 2 things. One, we haven't really made a lot of progress, I would argue, in multiplayer games. Like the same degree of success stories in games beyond 2 players or zero-sum that we can point to and say, look, we built really competent AI systems for these games. I don't think we have those. And I think it's for good reason. I don't think this concept of pi star is that useful to us anymore. I don't think the Nash equilibria provides us with much. For one, it doesn't give us the same way in a zero-sum game. It gives us a reward guarantee. It says no matter who you play, you're going to, say, win the game if you were playing a zero-sum game. So we don't have that same kind of reward guarantee. And these policies are not interchangeable, meaning if I were to take my component of a Nash equilibrium and you take your component of a different Nash equilibrium and so on, then we play them together. We're not necessarily in equilibrium anymore. And so it doesn't have the same guarantees. It doesn't have the same properties that we want. And I think the reason that we see this divide between, we've seen lots of successes in single agent settings, we've seen them in zero-sum settings, and we've seen comparatively much fewer outside of that, I think has to do with this way we move forward. And I think there's some underlying principles in this way we move forward, and those are what I want to question. OK, so let me walk through what I think is sometimes unstated. And I'm about to be critical here, but I should be careful because I'm critical of myself as well, too. I totally participate in what we're about to say. What I'm about to say is maybe the wrong way to do things. The first is that we break things up into, there's some notion of an agent training with the world. There's some notion of this training piece, and then out of that we extract pi star. And so there's built into this is this notion of the world acting like train then test. And like I said, I think we get this from supervised learning, that we do some interaction phase and then we do some evaluation afterwards. That's sort of baked into this. What's also baked into this is what we care about is an artifact, that we do this training phase, and what we want to pull out of that training phase is something the agent learned, and we're pulling that out as pi star being special, whether that's a neural net model or that's a set of values or policies or whatever we want it to be. That's what we're going to go and look at the end of this training phase. We're going to go poke at that artifact. And when we poke at that artifact, we then are future looking about it. We say, what can we say about this pi star? We could say, for example, it's a Nash equilibrium, or we could say, how exploitable is it? If we were to measure how close it is to a zero-sum equilibrium in a zero-sum game. And so we're saying things that are future looking about the pi star if we were to play this going forward. Lastly, once you take this approach and you take this basic idea of rationality we started with, then equilibria become prescriptive. It says that if I want to have a rational agent that maximizes reward with spectral beliefs among other rational agents, then equilibria are what must come out of this. And so we design algorithms that the pi star they produce are equilibria out of this. And maybe, well, all of those things are baked into this basic set of sort of principles that we often approach multi-agent RL with. So I'm going to contrast that with an alternative that I want to give, an alternative view that I want to give in the first half of this talk. And then from that, I'm going to then go into less hand-wavy sort of philosophical stuff and dive into some technical advances that we've had on the front that relates to this alternative view of rationality, which will be the sort of back 2/3 of the talk. Okay, so if we're not going to accept these basic principles, what's the alternative? Where else can we draw things from? And so, well, basically, I'm going to question all of them. So obviously, if I pointed those 4 things out, I've sort of pointed them out for a reason. So the alternative I want to call hindsight rationality. So the first point is that we're not going to talk about a train then test phase. There is a single lifetime that the agent experiences with the world. We don't get to break it up into phases. And we're just going to look at that single sequence of interaction is what we're going to care about. Secondly, it's the interaction that I care about, not the artifact produced at the end of that interaction. So hindsight rationality is going to argue that I care about the actual behavior that happens along the way and not something that I can extract out of that behavior. So I want to look at the moment-to-moment interaction, and rationality is going to appeal to that. Third, I don't want to be future looking. I'm going to actually make statements that are hindsight looking. They're going to say that up till now, we can look back and say this agent was acting rationally, rather than rationality being a statement about going forward. It's going to be a statement about looking back. And lastly, as a result of this, equilibria is still going to exist. We're not going to throw it entirely away, but equilibria is no longer going to be prescriptive. It's going to be descriptive. Kind of maybe where equilibria was intended to be from a game theoretic point of view as a description of intelligent behavior rather than a prescription of what we want. Equilibria are going to come back, and we're going to be able to say if agents have properties of hindsight rationality, then equilibria come out of as a result of that. Okay, let me try to walk through then how does this manifest itself. Let me give you a flavor of what this is going to look like. So as a starting point, let's actually look at what play might look like between 2 agents. In this case, there's only going to be 2 agents, but this is not a zero-sum game anymore. So we're going to look at Shapley's game. This is a modification to rock, paper, scissors. So hopefully you know the children's game rock, paper, scissors. But the modification here is that when you win, instead of winning from the other player, instead of them losing, there's really no losers here. There's only winners. In the places where you would see -1s, we just switch them to zeros. So it's almost like there's an independent source paying the winners $1, but the losers don't have to pay anything at all. So what this means is that losing, so playing rock while the other person plays paper, is no different than just getting a draw. Okay, so we have our zero-sum game here. Let's actually look at what would be a common dynamics of just a learning algorithm. This would appear if you were just using even plain Q-learning or any sort of policy gradient method. You would see dynamics that looks very similar to the following. Let's just suppose, due to some random initialization or some amount of symmetry breaking, the row player starts playing paper, and the column player is playing rock. So the row player is winning sort of initially. So what happens with the learning dynamics? Well, column player isn't going to be happy with the situation and is going to want to change. And so it's going to shift over to, instead of playing rock, it's going to shift to playing scissors so that it can start winning games. And now we're in the place where it's winning against scissors against paper. Now the row player is not going to be happy here and is going to shift from playing paper to rock so that it can beat scissors. And then that's going to cause the column player to want to shift, and they're going to shift over to paper so they can win. And then the row player is going to want to shift down to scissors, and so on until we get back to essentially where we started. So the learning dynamics is going to follow this flow, this pattern of learning. Now, notice the interesting thing about this pattern of learning is that it doesn't actually play on the diagonal very much. Now, it depends on the learning algorithms and how you do exploration and such. But in my caricature here, we're not playing on the diagonal at all. We're simply iterating through the possible plays that avoids diagonal play. To illustrate what I want to get at, we can now look at the actual pairs of strategies that the players are playing over time. So this is meant to be here sequence. This is player one's policies, we'll say. There's not much of a policy here in this single action game, but that's fine. And this is the column player's policy. And we're now looking at them over time and sequence over time. Remember, I care about one lifetime, and I care about the behavior itself. So if I was artifact-based, I might go and look at something like, let me look at what the row player is doing and try to extract something from that. And I could extract something from that. And maybe I look at their average of play. And I find that on average, if I look at their play, they play rock about 1/3 of the time and paper 1/3 of the time and scissors 1/3 of the time. I could do the same thing for the column player, and I'd find it too is playing this. Turns out this is a Nash equilibrium to have each player just randomizing, even in this modification of rock, paper, scissors. If I look at the outcome of that, it's actually telling me that the players should get about 1/3 of the time. If you actually play randomly, both players are playing randomly, then the utility to that row player will be about 1/3. But if you look at what the actual players are doing, I want to look at their actual behavior in their interaction, because their behavior is correlated. They're not actually just independently choosing amongst these average strategies. They're actually playing according to that colored graph there, where there's 1/6 of a probability that they're in each of the shaded cells, which means half the time the row player is actually winning the game, and they're actually getting a utility of 1/2. So when you look at the actual sequence of play, the correlated play is giving you a different utility. And the correlated play is saying we're actually winning about half the time. So that's the first point that I want to look at, is that if we're going to be behavior-based, we're going to care about the behavior, then we're going to actually be looking at correlated behavior of multiple agents learning at the same time. And that can often be very different than looking at trying to extract strategies from that. Okay, so what is this hindsight rationality concept? Okay, so the basic idea is I have a sequence of correlated play with another agent, and I want to look at, say, that row agent and ask, are they rational in some sense? Well, the sense that I want to look at is I'm going to define a deviation. I'm going to define an alternative to the behavior that they followed. And the way this alternative is going to manifest itself is it's going to be a mapping. It's going to map from policies to policies. It's going to say, if you were following this policy, what if instead of whatever you were thinking that was causing you to follow that policy, you instead followed this other policy? And so it transforms any policy into another policy. That's what one of these deviations looks like. So as an example, a deviation might look like just take any policy and map it to paper. So it doesn't even look at the policy at all. It automatically maps all policies to paper, or all policies to rock, or all policies to scissors. Each of those is a different deviation. And so basically the idea here is I could look back and ask, what would have happened if I just always played paper, just always map whatever I did to paper? And then the way I evaluate myself is well, okay, maybe my slides were telling me I was going to give you an alternative. A different type of deviation is one that actually looks at what we're going to do. Maybe it says every time I play rock, maybe switch that to scissors as an alternative. What I could have done as a possible deviation. So there's many types of deviations in the space. And the way I think about them is I'm just going to go back in hindsight and ask the question, how well would I have done if the sequence of behavior was instead apply phi to my behavior? So I'm going to uniformly apply it at every time step to what I did and compare how well does phi of my policy play against the policy that my opponent was playing. And if that would have done better, then there is at least an alternative form of behavior to what I was learning that would be better than what I did. And I'm going to call that irrational if I have such a deviation. So then we get rationality out of one more step. I want a set of deviations. Stephen, good question. And the answer is, of course, yes. And we're going to ignore that for reasons that it is hard to figure out. How behavior would have changed, one, requires some long-term predictive counterfactual that in general the agent can't apply. I think that is a potential limitation, so I don't want to just say we should just dismiss it. I think we're also stuck with, I don't think we could do anything about that without making assumptions about the other agent altogether. So it's going to be difficult, and we can make a fair bit of progress with this form to begin with. I don't know if that answers your question. But... Okay, so then to get a full-blown version of hindsight rationality, I go from a single deviation to I have a set of deviations. And the very notion of rational just means that I have no, with respect to that set of deviations I chose, I am rational if I have there's no benefit to me applying any deviation in that set in hindsight to my behavior. So that's going to be what my definition of rationality is. And notice that it is with respect to a set of deviations. So there's not one set in stone notion of hindsight rationality here. There you get to pick and choose by choosing your deviation set. These examples that I gave of deviations, they are, for example, they are examples of sets of deviations, right? These ones on the right, I'm going to call them blind deviations. That is true. Thank you, Franz. So I'll make sure I repeat the question. I guess for posterity, the question was, now I forgot what the question was. It was, wouldn't you, if you change your behavior, wouldn't it affect what the other agent would do as well too? And yeah, the answer, as I said before, was of course yes, but we can actually make progress with ignoring that. And I think it'd be very hard to make progress without having to know something about the other agent.
Great. Sorry for the interruption, but I thought you might want to.
Yeah, that was very helpful. Okay, so these examples of just mapping without even looking at the strategy we're playing straight to a particular policy or action in this case, we'll call those blind deviations. These other ones that actually look at what we're going to do and then transform it conditional based on I'm only going to turn rock into paper, those we'll call informed deviations. Now, I should point out that none of what I'm really suggesting here is really new. I mean, of course, it's not going to be new. If I make a small change to this, like let's just rephrase that slightly to there's no regret for any deviation in the set in hindsight. Well, like this is just online learning and regret algorithms. And yep, that's all I'm proposing. I'm just proposing online learning and regret algorithms. So if you're wondering whether what I was going to say was that groundbreaking, probably not. At the same time, I still see this really affecting what we actually do and possibly hindering us. And I think this view could actually be helpful. In the second half of the talk, there is going to be what I think is breaking some new ground in terms of regret algorithms, but we'll dive into that. It's also not new in the sense that, I had mentioned that equilibria don't exist here, and it's also not new in that sense as well either. If I call these blind deviations, we can now think of them in regret terms. We can call them external regret, which is the most common name. The informed terms in the matrix game sense is usually called internal regret. And we actually, in fact, know that if agents if we play a game where all the agents have no external regret or no internal regret, we actually get an equilibrium concept. We get correlated equilibria. Remember, I went back and said that when we look at the sequence of play, it's going to be correlated. Often we think about correlated equilibria as there's some mediator that's imposing correlation on us, and we can choose to listen to that or not. I think that's the less fruitful way to think about correlated equilibria. I think the way to think about correlated equilibria is just say, our interaction with other agents is correlated by definition. So then is there an equilibrium concept that relates to that? And that's what correlated equilibria gets us. And then it turns out that if you have no internal regret amongst all the agents, you get the exact concept of correlated equilibria. If you have no external regret amongst all the agents, you get coarse correlated equilibria. So basically every deviation set admits its own equilibrium concept. So rather than thinking about how deviation sets, like basically once you come up with a deviation set, by definition, there exists an equilibrium concept that says, well, it's what happens, that's what the agents converge to when they have that agents that are hindsight rational with respect to that deviation set, they're automatically going to converge to that class of equilibria. They're always just going to be a different class of correlated equilibria. Okay, I want to this was the first part, and what I want to sort of shift gears into, let's see if we can use this to go somewhere. But I want to pause and take a few minutes of questions just because we're going to walk pretty far away from this sort of very philosophical bit for the next 30 minutes.
If people have questions, feel free to type Q or question in the chat, and then we can go over them.
Yeah, Ed.
Thanks, Mike. So in your definition of hindsight rational, if you've got a temporally extended or repeated game, are you applying these deviations at any point in time, or do they have to be consistent across all the time points in that game?
As you'll see in the next bit, the way I'm going to look at this is I'm going to imagine that like you have a policy. If you have a repeated game, is exactly the setup I'm imagining here, and that the transformation happens on a policy like at the beginning of the game. You get to transform the policy that you'll use for that round of the game. I don't know how much we're tied to that, but I think we definitely need some much further technical development if we're going to go beyond that. And I'm not going to be able to do that today. So I'm going to focus on where imagine there are rounds of the game, and then the applications of these deviations are applied to your behavior on a particular round.
Thank you. That's great. Thank you.
Any more questions or comments on whether this like resonated with you or I utterly lost everybody? Because I'm curious. This is maybe the reason I think I wanted questions here was because I was really curious about how this would land.
France is one.
I have a question, yeah. And it's about the slide you have on, where you're trying to make this contrast, but somehow what is perhaps the biggest contrast here is not on the slide, right? The correlation. In the traditional rationality view, you can actually also, I guess, well, expand the problem or the game and try and find correlated policies through correlation devices of sorts, I suppose. So in this comparison, yeah, should you not take that into account in a sense?
Well, maybe I don't understand your question entirely, but it feels like if here the correlation is happening over correlation because our agents are playing the game together and my actions are influencing their actions, as opposed to as a sort of mechanism design player, I can impose some notion of correlation on the agents. In which case, then I'm not sure the rationality statement is about the agents themselves. It's about some other third-party agent that's getting to design some mechanism. So I am looking towards some way of understanding rationality on the individual agent's decisions part, which I think is different. Now, correlation, like you said, does come out of this. I sort of viewed it as being artifact-based or behavior-based in my description, that once you look at the behavior itself and how we're interacting, then kind of by definition, you have to think about correlation.
I see. Yeah, I guess I was viewing it more as kind of like a system designer, and you know, there's this traditional route that I might want to take, right. Somehow produce some policies and deploy them, and now Michael comes and says, well, no, you need to go this other approach. But
yeah, if you're in the system design point of view, then this next part of the talk, like the setup maybe doesn't resonate with you, but the next part of the talk is still very relevant, even though I'm coming at it from I want to design agents that have a particular property. What we're going to build in the end is a whole bunch of different new correlated equilibria concepts. And I think they could be very relevant because they're by definition tractable, because I want to do them for our agents. So a mechanism designer could do them for mechanism designs as well too.
Yeah, clear.
Christian.
Hey, Mike. So first, I just want to say definitely a very nicely motivated setup that you're giving here. I want to ask if you have any thoughts on sort of the CS theory view that I feel has a somewhat similar sort of idea over the last 10 years after, general sum Nash equilibrium was shown to be PPAD hard or complete. A lot of CS theory people have really sort of argued for regret minimization as a more descriptive notion of actual play. And so I'm wondering if you have any sort of thoughts on, there are certainly parallels between what you're suggesting here and that. I'm also wondering if you have any thoughts on sort of differences between the two.
I think I would have to hear more of the specifics. I don't think I have any immediate thoughts on the differences. From what you said, it sounds highly aligned. Yeah, I don't know that. I don't know have any immediate jump to any differences. It might be that we're pushing in the same direction.
Okay.
Okay. Let me jump on to some new technical stuff that's built out of this. And I have lost my slide advancing ability. There we go. Which means that if we buy into this, or even if we don't, and we buy into a mechanism design view, then there still comes a question of everything starts to revolve down to, well, what's the choice of deviation set, right? I'm basically creating a whole family of rationality measures. So then what deviations, what's a good set of deviations to pick if we want to evaluate an agent, determine if it's rational or not. But also notice that this whole setup gives you a way of doing agent design as well too. Not that we can design algorithms by picking our deviation set and then seeing whether we can build agents that can minimize their regret with respect to deviations in that class. And so then kind of by definition, there's going to be now a trade-off. There's going to be a trade-off between, well, if I have a lot of deviations, if I have a lot of the capacity of possible deviations I consider is very large, then I have a lot of power. That means that the rationality concept is going to be stronger in some sense because there's more deviations that I am ensuring that I don't wish that I had followed. On the other hand, more deviations is more computation. That could be more memory because I might have to remember regrets with respect to them. It might be more interactions. The more deviations you have often from a regret-bound term, if you try to actually minimize them, you actually often need more steps before you can pull the regret down. So lots of deviations isn't always in your favor because you have this trade-off. And we've sort of seen this trade-off a little bit already. The set of external algorithms, there's A of those. There's sort of number of action size, order A of those of deviations. Whereas on the internal side, there's order A squared. And in fact, the internal ones sort of do subsume the external ones. So seems like there's just a trade-off here. If you wanted a more powerful algorithm, you could go to more order A squared, but it is going to cost you something. Maybe you want to stick with the simpler ones. It's not clear which one you would choose. But that's only if you can't use structure of the problem to somehow get the best of both worlds. And in some cases, you can get structure to get you the best of both worlds. Okay, so let's actually look at structured problems. I motivated everything with being sort of, there's no sequences of actions in our decisions. There's just one action, and you take it simultaneously. You're playing a matrix game. But the interesting cases, and where a lot of this becomes very interesting, is when you go into a sequential decision-making setting. I'm going to sit on top of extensive form games, which just means that there's going to be a repeatedly play an extensive form game where we make a sequence of decisions with another player. Possibly we don't share full information, but I'm going to represent one of the decisions of a player as a tree. So I'm really only focusing on one of the player's decisions. And so the tree sort of captures what decisions they get to make. So, I could go left or right, and then I could go left or right again. Maybe one of those one of those sequence of actions results in an end of the game, and I get some utility. I'll sometimes draw a triangle to mean there's a whole bunch of decisions under there that myself and the other agent might be making before the game terminates. And I'll just draw a triangle to summarize that. There's like a whole policy being employed under that triangle. Sometimes I'm going to draw a jagged line of actions here before I get to like some point where I'm then going to draw a triangle to say now there's a whole policy that happens underneath there. And under the sequence of actions, there's of course all kinds of branches coming off that sequence I'm not drawing. And so I just want to give you a feeling for what these drawings are going to look like because I'm going to use these drawings a lot. Okay, so let's start to look at what are possible deviations that we can think about. So one class of deviations we could think about would be blind strategy deviations. So these are just like the blind deviations I talked about before. It says, without even looking at what strategy I was following before, just pick this strategy and do that. And so it just blindly adopts a fixed strategy, regardless of what I was doing on that round. So I'm going to use green to denote that I'm deviating to something, and black's going to denote when I'm just following whatever I was doing before. In this case, I don't follow anything. I just replace my entire strategy with the deviation. The slight problem here is there's a lot of those. Like if you think about every possible way I could play the game, well, if the I is going to be the number of information sets or states, if you like, then I have an exponential in the number of decision points, number of possible strategies I consider. So this seems like a really big class if I were to implement this very naively. On the other hand, once we're in a sequence of decisions, I could think about like blind action deviations. So the idea here is I'm going to pick a particular state or information set, and I'm going to assume that I follow whatever my policy is until I get there. And once I get there, I'm going to take a very particular action. Regardless of what action I was going to take, I'm going to switch to this other action. And then after that, I will follow the policy, whatever it was going to say from there on out. So I'm just going to take a particular state and switch the action to a fixed action, which is one action in my policy. Nice thing about this is there's not that many of them. There's only a number of states times number of actions, or number of info sets times number of actions. So we might think that the blind strategy one is much more powerful than the blind action one. But it's actually not true. Blind action can actually, like, you can actually have no regret for all your blind strategy deviations and still have regret for a blind action one. And I'll show an example of that in a little bit. So neither of these subsume the other, that they're wildly different in size. A different class, yeah, so you might think that blind strategy implies that. It doesn't. Another class might be one of the popular algorithms in extensive form games is the counterfactual regret minimization algorithm. We can view that as minimizing a particular form of deviation, as minimizing regret with a particular form of deviation set. And the deviation set consists of pick a particular state and try to play to that state. So pick an information set and drive as best you can. Take every action that's consistent with reaching there. Obviously, if the player plays so that you can't reach there, then that's fine. You just do whatever. You go back to following your policy. And once you get there, to start following your policy. So the deviation is to force yourself to reach an info set. And those consist of the counterfactual deviations. It's exactly what counterfactual regret minimization is minimizing. It's minimizing its regret with respect to these. And it turns out that there are order a number of information set times number of actions, number of these. So that's handy because it's tractable to keep track of this. What's really surprising maybe, or was at the time, is that blind counterfactual, if you minimize your regret with respect to blind counterfactual deviations, you actually guarantee to minimize your regret with respect to all blind strategy deviations. This was the CFR theorem from 15 years ago. That was really the power that drives CFR. Is that even though these two sets of deviation classes are wildly different in size, one entirely subsumes the other. And this is why CFR is arguably so powerful. Okay, so that's cool. Sometimes the trade-off doesn't have to go so bad because we can exploit the structure of our environment so that we don't actually have to enumerate everything. There is another class that has been studied also about 10 to 15 years ago, which are causal deviations, or I'll call them blind causal deviations, because again, we're not going to trigger on any particular action we're taking. So here the idea is it's sort of the opposite of counterfactual deviations. I'm going to actually follow whatever I'm doing until I reach a particular information. From that point onwards, I'm going to take over and switch to a new policy. So these are blind causal deviations. You might think that like blind causal deviations seemingly are more powerful again than blind action deviations, because hey, when I get to a particular point, I don't just switch one action, I can switch an entire policy. And it turns out that's not true either. I actually want to walk through some of these counterexamples. The paper that's up on arXiv has all of these counterexamples in it, but I want to walk through some of these counterexamples because I think they're enlightening. Okay, so the first counterexample that's going to show that result, that if you switch to whole policies versus whole actions, they're not the same thing. And so we're going to take the Bach-Stravinsky game, sometimes called the Battle of the Sexes game. Two people, they're both going to choose which concert they go to. They can go to the Bach concert, the Stravinsky concert. They'll do it simultaneously without knowing the other player's choice. If one player might choose to go to Bach, and if the other player also chooses to go to Bach, then they get some payoffs. And the left player, they're very happy because they got to go to the concert together. They'd rather be with people, I guess, socially distanced. They'd rather be separate, but whatever. So here they're happier because they went to the same concert together, but the left player prefers Bach, so they're a little bit more happy. Alternatively, they could both go to Stravinsky, and then again they're happy, but the right player is a little bit more happy. If they end up going to different concerts, then neither of them are happy because they didn't get to meet up with their friend, and they get zero utility. So that's the Bach or Stravinsky game. I'm gonna have a modified Bach or Stravinsky game. In this game, one of the players gets to choose ahead of time. Are they going to go out for drinks afterwards or not? So that's their choice. They get to decide that, and then they're going to choose Bach or Stravinsky. None of that is revealed to the other player. So the other player is, again, simultaneously just choosing Bach or Stravinsky. And the payoffs are such that if they choose not, well, let me actually go back. If they don't choose to go out for drinks, if that player who's choosing this chooses to not go out for drinks, then it doesn't change the payoffs of the game at all. They're just playing Bach or Stravinsky now. But if they choose to go out for drinks, and they end up at the same place, they both get an extra utility for enjoying the drinks afterwards as well as the concert. If they end up at separate places, well, there's no one to go out for drinks with, so that's pretty boring, so they don't even go anyway. So they're back to 0. So the drinks choice seems like just an obvious one. Like, hey, if we end up in the same place, we'll get even more utility. So that's what the game looks like. Okay, so now let's actually look at a player playing this game. And we're going to look at correlated play. So I'm not going to show you the whole sequence of play, but to simplify things, I'm going to imagine, say, on even numbered rounds, the play looks like this. What does it mean? The bold lines are the ones that have actually happened. So this is showing the player who's choosing whether we go out for drinks or not. And they decided on the even rounds, they're going to not go out for drinks, and then they're going to choose Stravinsky. And it turns out the other player on the even rounds also chooses Stravinsky, and so they get a utility of 2 under that case. On the odd rounds, the player is going to choose to go out for drinks and then go to Bach. And it turns out the other player on the odd rounds also chooses Bach, so they get a utility of 2. So this is trying to show you the whole sequence of play just by broken it up into even and odd rounds. So the utility of this policy is 2. And then we can ask, well, is this sequence of play rational for the player? Meaning, is there a deviation that they would rather have? So it depends on the deviation class. Let's look at the class of blind action deviations. So the blind action deviation is just say, pick a state and switch one action, and that's it. So I'm going to switch the action at the very first state to say, go ahead and choose to go to drinks. And now you do this in a blind way. So you do this in both cases, both the even and the odd rounds. And so what's happening here is I'm just changing this action. So now the outcome in the even rounds is I go for drinks. And then before, if I did go for drinks, I was going to go to Stravinsky anyway. So I get a utility of 3. In the odd rounds, drinks, and I go for Bach, and I get a utility of 2. And my payoff is 2.5, which means that there is a profitable action deviation that I would like to take. If I look at strategy deviations, or actually, let me just jump to causal deviations. Causal deviations can't do this because when they force you to take the drink action, they then have to replace the policy underneath. And if they replace the policy underneath, they have to pick either always go to Bach, in which case I get 2 on odd rounds and 0 on even rounds, or after I choose drinks, go to Stravinsky and I get 3 or 0. The best I could get is a 1.5 on average, so it's not profitable to make the same kind of deviation. And the reason is because causal deviations can't cause recorrelation to happen. Once I've broken correlation by taking a deviation, I can't let the policy recorrelate again. And it's because of that picture, right? The picture is I have correlation happening, switch to a policy where we forcibly decorrelate, whereas blind action deviations can recorrelate again after taking the action. Similarly, CFR algorithms can also avoid that problem where you can recorrelate afterwards. So we now know that there is no blind causal to blind action. It is trivial that blind causal implies blind strategy because I can always just deviate right at the root. There's another question. Does blind counterfactual sort of imply blind causal? You can find drafts of papers where people suggested this was true. You can find an email from me with a PDF that contains a proof that is wrong. It turns out it's not true. Blind counterfactual doesn't imply blind causal. Given time, I think I might skip this one. There's a modified matchy pennies game that illustrates that you can't get this. And basically the problem is essentially just the reverse. That in the one case, in the blind causal case, the problem is it can't recorrelate. The problem with the blind counterfactual case is it can't keep initial correlation going before it then makes a deviation. And so that's the limitation that counterfactual has. Now, what about the size of these sets? We pointed out that these sets are much smaller. So we have this sort of setup. This is what we in fact know. And in fact, no other arrows exist in the blind setting. There is that you can do. We can actually show counterexamples to every other possible implication on this. So if we were to just look at this class of deviations, which should you pick? It's not obvious, right? We probably don't want to pick blind strategy ones because there's a lot of them, and we can get better by just looking at counterfactual deviations. But otherwise, it just depends on which sort of different hindsight regret properties you want. Now, maybe you prefer the order AI ones. It turns out that blind causal I think Andrea Celli's on the call and on the meeting. They have a recent paper that shows that you can actually do this. It does require, I believe, he could correct me if I'm wrong, I believe it requires memory and sort of regret time that sort of has a depth term associated with it. So the deeper the game is, the more costly this is going to be, whereas these don't have depth terms associated with them. So maybe there's a reason why people have been running counterfactual algorithms outside of the zero-sum setting and found them doing interesting things. And I think it might be because they have these regret properties. One more thing is I mentioned every deviation set basically admits its own equilibrium class. So if you care about equilibria classes, then we have equilibria classes. This exists in the literature already. Blind strategies get you coarse correlated equilibria. Blind action strategies get you agent form coarse correlated equilibria. Blind causal get you extensive form coarse correlated equilibria. We then just say, well, if you want to know what blind counterfactual gets you, it gets you counterfactual coarse correlated equilibria as being the very thing where no agent has any counterfactual deviation regret. Okay, it turns out you can do all the same thing with informed deviations. You can go explore the same set. There exists as informed action deviations, informed causal deviations, informed counterfactual deviations, where instead of just always deviating to a particular policy, you do it based on having a triggering action. There are implications. Informed strategies, for example, basically say, if I'm playing this strategy, I look at the entire strategy and I entirely map it to another one. This is the most powerful class, really, that you can have. This, of course, implies all three of the other ones. Informed always imply their blind equivalents. So we sort of have implications going off on the other slide. These keep implying down the chain. One problem, though, is the informed strategy deviation class is enormous. Like, it's totally impractical. It is the most powerful one, but we're kind of sunk in being able to run it because we're going to be exponential in the number of decision points we have to begin with. And as far as we know, there's no structural advantage that you can have to take advantage of that. But is there something in between? So let me jump to this last part. I'm sort of running out of time here from what I wanted to say, but let me actually point out that there's something in between. So this is the paper that's not out yet, that we can actually go a little bit further than these existing deviation sets. And the little bit further is introduce a new deviation class. These are going to be blind partial sequence deviations. In some sense, they're very natural. They're just going to look at what counterfactual and causal can do and do both. So essentially, like causal, they're allowed to follow and stay correlated for a bit. They'll reach some information set, and then they're going to force themselves to deviate to take a particular action sequence to reach another information set, and then they'll stop, like counterfactual, and then let the policy take over again. So these pretty clearly just imply the other three. So blind partial sequences pretty much by definition get you the other ones for sort of obvious reasons that they can subsume those. But the nice thing about this is their actual number of regrets you need to keep track of to actually implement this is only a depth factor times number of actions times number of information sets. So they're almost the same costliness as blind causal deviations, but you get this more powerful set that subsumes all the other ones. The algorithm that does this is actually even more general than this. We call it extensive form regret minimization, or EFR. The algorithm actually can operate on any structured set of deviations. So the same algorithm, if you hand it the counterfactual deviations, CFR comes out of it. If you hand it the causal deviations, if you hand it the causal deviations, a version of Celli's algorithm actually comes out of it. If you hand it action deviations, it will do an efficient version for blind action deviations. You can apply it to their informed sets as well too. In this case, you end up with the most general class that we can handle are these twice informed partial sequences, where you have some trigger at the beginning and a trigger at the end. We have the trigger at the end mostly because it costs us nothing to add it, and the sort of cost is that we end up with an a cube term with a depth term on the front of it. There's one more class I want to show really quickly here, which is actually in between that truly enormous class. This is still it's not exponential in the number of decision points. It's still bad because it's going to be exponential in the depth. But we can talk about behavioral strategies, which basically allow you to deviate at every point along the way based on the recommended actions you've seen so far. I only mention that because I want to show some. I want to end the talk with showing some results. So this middle bit of the talk was mostly about, can we understand how these deviation classes relate together, and which ones are efficient and which ones are more powerful than others. But you might want to ask, well, does it matter? Can empirically this do anything interesting at all? So we have some experiments, again, in the second paper that unfortunately is not out yet, but will be soon, where we basically ran on, I don't know, a half dozen different games using lots of different agents. We sort of built a tournament where we built both, imagine having, like, doing simultaneous learning together, but we also did some structured tournaments where we just had fixed sequences of behaviors of other agents and looked at who could adapt to those fixed sequences quickly. So I want to show some results from that, just to give you a flavor of what these results look like, because they largely line up with what the theory says. So this is in one of the games we looked at, was Goofspiel. I'm not going to get into the details of the game, but what we're looking at here is there are fixed opponent strategies, and we're looking at each of these agents, how fast can they adapt. When I say fixed, I don't mean that their strategies, they are following a fixed sequence of play that is adapting, but it's not necessarily adapting to the agent playing. So that this issue that Stephen brought up at the beginning, where does my play affect yours, we've taken that out of the picture. There is simultaneous results in the paper as well too, but I'm not going to focus on those. So the action set, the blind action deviations, in fact, these are the informed action deviations, they actually get the worst performance over time. They're the not as good as the counterfactual ones, which are the lines shown here. But if you go to the new classes that we added, which are shown on the right, these are the blind partial sequences. They're about in line with the counterfactual ones, even though they're technically stronger. These are variations on the twice informed ones, but then the twice informed one is a step up from that. And the behavioral one, which is the most expensive tractable thing we can still do, and it's on the edge of tractability, is the best of all of these. And so these stronger, as you get progressively stronger, you in fact do better in real empirical results. This is a variant of the game Sheriff of Nottingham, a small version of it. And the same thing that we see, action deviations are the worst, counterfactuals improve on that. And in fact, counterfactuals with informed deviations are the best in terms of that class. If we look at the more computationally complex ones, then as we go up from blind partial sequences all the way up to twice informed partial sequences, we get better, and behavioral sits on top of that. And so we can actually see these things having empirical advantages as well too. Okay, I'm going to end there and switch to questions. Just to remind you, part of this was motivated by changing our traditional view of thinking about train then test and pulling out artifacts, and instead looking at single lifetimes. I think we have a much better of how sequential behavior, how we can build deviation classes on top of sequential behavior. And we've even seen some results that shows that empirically we would care about this. Cool. Thank you so much for your time, and I'm really happy to take questions.
Thanks a lot, Mike, for a wonderful talk. So
I see there's some questions already in the Q&A.
okay, very
Do we
cool.
want to have people read out their questions, or
Yes.
or should I read them out?
I would say the people who pose the question, unmute yourself and quickly ask the question.
Franz, do you want to go first?
Yeah, sure. I guess obvious question. So you are offering all kinds of options here. You know, pick any deviation, and we can try and minimize regret with respect to those deviations. So yeah, what should we really do to some extent? You started talk saying, well, Nash equilibrium.
Right. I think my answer right now is twice informed partial sequence. I say that because of the trade-off between the power you get and the cost that you get. So behaviorals still have this exponential in the depth cost, which probably in most situations rules you out. The twice informed partial sequence is on all the terms that we might typically care about, which means that it is the richest class that we know of that we can that subsumes all the other ones that we know of, while still being polynomially strong. Now, if your action set,
my agent encounters some other agent of somebody willing to spend more computational power, So how does this not just lead to, I guess, this battle of computational power?
I don't think it avoids that. Sure, I think you're probably right. I think that there is a sense in which, I mean, that's what these results are showing, because what this tournament essentially was like what happens when you play against agents that are using different deviation concepts. Ones are doing poorly. So if that's all the computational complexity you could afford, then you're going to pay for it and how well you can do. I'm also not sure that that's a bad thing. I mean, if you really want, like if we wanted to have the one, deviation class to rule them all, I suppose you could just point to informed strategy deviations as the ones that subsumes all the others. But the problem is that we just don't have the computational power to do that. So I think bounded rationality is exactly built right into this, that your boundedness tells you what class you can pick.
So is that then perhaps a next step to make explicit somehow the computational cost?
Well, we certainly have it for EFR. Will give you what the computational complexity is once you, depending on the structure of the deviation sets, the set of deviations you give it. So I think we understand it for most of the classes that we've been able to think about. You sort of asked what next. I'm going to tilt it entirely from your answer to something else. I think there's some pieces that are obviously missing. One, this is all sitting in a very tabular form, and as we go to large scale systems, we tend not to work in tabular forms anymore. And then what happens? Like, can we, in the same way that we can have regret motions still when we're in non-tabular classes, we'd like to figure out how we extend these into non-tabular settings, and I don't know what it looks like yet. I'd also like to figure out how to extend it away from being these sort of fixed, repeated sequential settings into the more, I argue that it should be lifetime, but in a real lifetime, we don't necessarily have these episode boundaries, but this is defined very strictly with episode boundaries, which is also a limitation. Stephen.
Yeah, thanks for the talk. This is great. So my question is, what do we do if we want to achieve superhuman performance in multiplayer games? And is this even a goal that makes sense? If not, what should sort of be the goal when we're actually trying to interact with the real world?
I have what I would like the answer to be, but I also practically know that that's not, we're not at that point yet. I feel like a fair test of superhuman performance is not typically what we do. And in fact, you've seen this in certain cases where, like the very early 1v1 Dota work, when they put it out, right, that they were, day one, they were declaring superhuman performance. They were crushing all the pro players. And day two, amateurs were able to crush it doing very silly things. And so, like, you really do need to look at lifetimes, I think, to really declare anything. But on the other hand, that creates its own challenges from an evaluation point of view, where we don't have lifetimes to be able to let people adapt to what anything is doing. Once we were in that setting, then we should let our agents adapt. And then it really is like the lifetime behavior view that is listed here, right? Like, I think if we really did that, if we really said, humans are allowed to adapt to the agents should be adapting to the humans, because it's of course not fair if we take our agents and fix them and let the humans find flaws. But that is almost how no tournament is set up, right? If it's AlphaGo and we run 4 matches and we declare a victor after 4 matches, and that is not a typical lifetime setup. So the answer I'd like it to be would be, we let these things run. I think the reason that's also not practical is it takes too long to do that from a human point of view. I think it's also not practical because our agents can't learn fast enough, right? Like, if my view is right, I should just be able to take a twice informed partial sequence EFR algorithm, and it's just going to sit down and play whatever game for the first time, and it's going to learn to beat humans as it plays over its lifetime in some sense. But we don't have fast enough learning algorithms that can do that.
Yeah.
So,
and also, if I knew the learning algorithm, you would be able to know exactly what the agent would do, right?
Not these twice informed partial sequences. What they have to do to make sure that doesn't happen is that they're stochastic in just the right way. Like, this is typical of like the external regret algorithms, right? Like, what we can do this is in matrix games. So if you run an external algorithm in a matrix game, you won't find a way to beat it because we get out of this. So the problem is, as we scale the game up, our techniques don't they go slower and slower and slower to be able to cope with the size of the game. Like you can see it in these order terms I'm throwing out there. If one of those points is the number of states. And so that's great when you're talking about a matrix game with one state. But if you're going to talk about, a game that humans actually play and care about, where it's 10 to the X states, where X is a, big number, then depending on that or having memory order that is out of the question. So I feel like this is suggesting the right idea of how we do this, but it's just not practical right now. You asked, does that goal still make sense? I mean, I think it does. I think it's still interesting, but I think we also should caution with a grain of salt that I don't think in the zero-sum case, I think it is more meaningful. In the single agent case, it's much more obvious what it means if you were to just say, I got a higher score than any human's ever gotten before. But once we're adapting to each other, things get a little bit weird. And we've seen that in poker too, which is why for a long time, the poker community pushed on exploitability as directly measuring how suboptimal you are. Exactly because play against humans doesn't always tell you whether you're a better player.
Thank you.
Thank you for the interesting talk. I'd like to follow with the question about if the other agent, if the opponent is also doing the deviation strategy. And I was curious whether if the other agent is doing the deviation, is thinking about I'm doing the deviation. And I was curious whether that would result in nature infinite recursion, similar to the infinite recursion happening in the theory of mind.
So first, I want to say that one thing that is happening here is we're making a property statement about agents. We're saying an agent is rational if the following thing happens. If I look back on its hindsight play and I can see this being true, then that sequence of behavior, we could declare that being rational. Now, I shifted from that to we could design algorithms to achieve that. And I think you're sort of now focusing on that last part. So once I've designed my algorithm to achieve, could someone build an algorithm that explicitly tries to take advantage of that? So in one sense, the answer to that is a little bit, I want to say it's a little bit no-ish, depending on what you mean by take advantage of that. Most of these classes, if we look down to these classes, all of these point upwards, like all of these classes imply they're blind ones. So that means everything on this chart except for blind action and informed action all sort of feed into blind strategy. And if we think of what the blind strategy class is saying, it's saying, I'm doing as well, like there is no other fixed strategy I could have played over time and done better than what I did. Which is a pretty powerful statement that kind of says that I don't need to, like, I'm protected from someone outthinking me because the class already sort of covers me a little bit on, there's no fixed strategy that could have done it. Sure, there's some changing strategy that maybe could have done something, but that, and I could get into that arms race, but this in some sense cuts that arms race off at the knees a little bit, saying I can make guarantees that don't have to worry about that. I don't know if that fully answers your question.
Yeah, thanks for the clarification.
Alexander.
Yes, hi. Thanks for the nice talk first. And so my question relates to the deviation. And okay, I'm currently looking a bit more into causal inference and how it relates to reinforcement learning in particular, and maybe also multi-agents and whatnot. But so at some point, of course, everything looks like causal inference. But in particular, the deviation, it sounds like it's a class of possible inference interventions at action level or maybe at policy level. Is there a relation to that, or am I getting something wrong there?
I think there might be. Here, this is a slide I was thinking of, but
Exactly.
I feel like the connection I see, which we're both in a place where you know way more about and interventions than I do, and I know something about this that you don't know, and we're both maybe the intersection is maybe not the best. Yeah. But I think what you might be driving at is goes back to the very first question, the first clarification question, which is wouldn't deviation behavior affect the opponent's play, right? Like if I actually did phi at time 2, phi of pi r2, that's going to affect pi c3. It's not going to be what it was, which means that we could try to understand that inference process. Like if I wanted to build a model of how the other player would respond to my choices I feel like you would want to follow down this causal, to try to build an understanding of how does the behavior of the other agent, how does my behavior affect that? And I'd want to build causal explanations of that. And these fees would then become interventions to figure that out. Like if I did this, would that have caused the future sequence to be different? But that wasn't quite what you were driving at, but that's the connection I first see in my head.
Okay, I see. Yeah, for me, I don't necessarily think about the how it affects the other players. We could imagine that for fixed, but for me, this fee seems a bit like, you call it also hindsight rationality. Like to me, that seems like counterfactual reasoning. What would have happened if I did this?
Yeah, I mean, there is I think there is a question that I entirely dodged that you could be driving at right now, which is, I say, look back in hindsight and ask, would you have benefited more? Would you have gained something from applying this deviation? Exactly. And that requires you to be able to look at this term right here and say, what would have happened, even on that round? Forget about like the way Stephen asked the question was, wouldn't my change affect the future? But my change is also, if I play a different policy, then that outcome of the game is of course going to be different. And can I even measure that? Like, can I even answer the question, if I had applied this deviation, what would be my resulting utility on round 2? And under certain circumstances, you could do that. If it was a matrix game and players' actions were announced, then it would just be, and the matrix game was known, then you would be easily able to do that. I would just say, well, I'm going to switch this action. Let's look at the matrix game. What would have happened? In a sequential setting, it isn't as obvious anymore. But I think we're sort of, I don't view this as a problem because in the bandit literature, we all know that we can solve bandit problems where I don't get the value of every arm pull on every time step, but I can still ask questions and infer results of what would have happened if I had pulled it by just periodically pulling that, which is maybe another place that you mean this by interventions of saying what we're like. One way to analyze that is to actually apply the fee and see what would have happened. And if I do that on a stochastic basis, I can actually estimate what I would have gained if I had been applying the deviation over time.
Yeah, the problem and the explanation seems again exactly like the problems with computing counterfactuals and causal.
Yeah, I agree.
Yeah, I guess there's some. Okay, thanks.
Maybe we should move to our last question.
Was that the last question, or was there another one?
No, I think there's one left. I think
there's one more.
Left. Yeah,
Z2.
if that's okay with you.
Yeah, it's fine.
Hello, Michael. Thank you for your talk, and I think it's very inspiring, and I really like the experiment result you show. I think they are quite meaningful. And my question is just, if it's always expensive to consider some deviation set, for example, the one you mentioned, the information twice, something, I forgot the name, and then is it possible like we can find a rule that we only consider those expensive set at some time point, and then because we have a limited rationality, then we consider less expensive ones at some other point because we are considering a lifetime setup?
Yeah, I think this intuition is a really great intuition that even, for example, actually, let me go back to the other slide here. If we think about blind partial sequences, a slightly different way to put this might be, one of the reasons we added that D term in there was because the length of that partial sequence can grow in time. If I don't allow it to grow in time, I were to say, no, I'm going to only allow partial sequences of length 2, then that D just becomes a 2. And so, that's a place where I actually have some leeway to say, I only want to consider deviations that are of a particular length. Now, if I actually break that, then I don't get the implication that blind partial sequences give you blind counterfactual sequences, which might mean that I don't necessarily, I lose the connection to blind strategies. So there's definitely something lost here. I think a different way to think about it that I think would be interesting would be, what if the regret guarantee I have is sort of adaptive in the following sense, that deviation classes that have a long depth of the partial sequence, I'm willing to tolerate more regret with respect to them because there's many more of them. And for ones that are very short, I want to tolerate less regret with respect to because there's many fewer of them. And so this notion that your regret with respect to the entities in the class would not be uniform, I think is a way forward that could be really powerful, that could get you into these more richer sequences that are more expensive by thinking about, sure, there's way too many of them to do them uniformly, but maybe I don't have to do them uniformly. Maybe I focus more on the ones that are simpler and there's fewer of them. And this isn't the only place that you can see these sort of adaptive style regret bounds. But I think taking that idea, I think would be really cool.
Okay, yeah, thank you very much.
Awesome. Thanks for the great questions and great discussion. I think we need to thank Mike again for a wonderful talk. It was an amazing first session of the series. And I guess we hope to see everybody again in 2 weeks from now for the next one. So thanks a lot, everyone.
Thank you, organizers. This was super fun.
Bye-bye.
Thanks, Mike.